So, I mean, this seems like a pretty straightforward question, right? What's the fourth root of 1? The obvious answer is 1, right? 1 to the fourth power is 1, so yeah, okay. And if you wanted to stretch it, I know you're always taught, right? Even roots, just take the positive 1. But I mean, you could make an argument for -1. But here's the problem. Okay, here's the problem with that. Let's say I make this into an equation. X equals the fourth root of 1. And we'll raise both sides to the fourth power. X to the fourth equals 1. And then subtract 1 from both sides. X to the fourth minus 1 equals 0. Okay, now we have a problem. This is a fourth degree polynomial equation. And the fundamental theorem of algebra says that a fourth degree polynomial equation has not one solution, not even two solutions. It says it has 4 solutions. There are 4 solutions to this equation, which means there are not 1, not 2, but 4 fourth roots of 1. I'd like to know what they are. All right, that's what we're going to be able to do. All right, that's what our new polar form of a complex number is going to let us do. All right, so here's kind of the first step. So here's how we're going to approach this. All right, and here's kind of the setup. All right, we're starting off with 2 complex numbers, z1 and z2, and they're written in their polar versions. All right, so z1 has radius r1 and angle theta 1. And z2 has radius r2 and angle theta 2. Okay. So if I want to multiply these numbers together, right? I mean, we know how to do this. You can do the FOIL thing, kind of multiply it out, right? But turns out if we have them written in this polar version, there is a much quicker way to do this, right? To multiply the numbers, all I have to do is multiply their r values and add their angles. And to divide them, all I have to do is divide their r values and subtract their angles. Right? And that's all there is to it. All right, so let's look at an example. Right, and I already have the numbers written in their polar form. Right, I've already broken them down that way. You kind of figure out what these are if you want to see the original numbers. Cosine 30 is cosine 30, square root of 3 over 2. So this is 3 square root of 3 over 2 plus 3 halves I. And doing 60, this is square root of 3. It's 2 times the square root of 3 over 2, which is the square root of 3. Plus, well, whoops, sorry, this is 2, cosine 60 is a half. So this is 2 times a half, which is 1, plus 2 times sine 60, that's the square root of 3 over 2. So this is the square root of 3i. I want to multiply these things together. Well, if I wanted to do it the old-fashioned way with the FOIL business, right, I'd have all those square roots of 3 to keep track of, and then, of course, you've got the I squared, and you got to make that minus 1, and yeah, okay. But look, I got my new formula. Right, I got my new formula. Look at Z1. R1 is 3, and theta 1 is 30. Looking at Z2, R2 is 2, and theta 2 is 60. So come up to my formula. My formula says multiply the r's together. 3 times 2, and add the angles. Cosine with 30 plus 60, that's 90, plus I sine 90, those are degrees. Cosine of 90, that's 0. Sine of 90, that's 1. 3 times 2 is 6, so the product of these numbers is just 6i. And that's it. Right? Really simple. Much simpler than it would have been to do this with the FOIL method. All right, so let me give you one, right, to work with here. I mean, I've got 2 complex numbers. And yeah, okay, this time they're not already written in the polar form. So that's going to be your first step, right? Find the polar version of each of these numbers. And then I want you to find their quotient, right? Use this formula to determine what the quotient of the two numbers is. Okay, so where you should have ended up over here, right? Z1 is 3.606. That's the square root of 3 squared plus 2 squared. So what, the square root of 13? Cis, I'm going to use my shortened notation here. Cis 33.690 degrees. And for Z2, this would be square root of 25 plus 16. That's what, 41 is going to come out to 6.403 cis negative 38.660. And I'm fine with a negative angle here. The 5, if you go to over 5 down negative 4, that's in the fourth quadrant. And yeah, that negative 38 degrees, that is a fourth quadrant angle. So yeah, I'm fine with that. Okay, so now we're going to use our formula. Right, my formula says that 3 plus 2i divided by 5 minus 4i is 3.606 divided by 6.403. Cosine, and I need the difference. Now you got to be careful. You do have to get these in the right order. The angle, the number on the bottom is the angle that gets subtracted. So this is, let me do the cis thing here. Cis, this is 33.690 minus negative 38.660. Make sure I got all my parentheses right. There we go. Okay, now you go to your calculator, right? This is 3.606 divided by 6.403 cosine 72.35 degrees plus I sine 72.35 degrees. And okay, now I'm going to go to my calculator. This is 0.303 minus 0.537i. And that's it. Right, that's it. That's all there is to it. Okay, so what's next? We're almost there. Now, so far, it's arguably easier to just multiply things out or just rationalize the denominators. Right? It's not so bad when you've only got two. In the next presentation, we're going to look at something called de Moivre's theorem. It's going to give us a really quick way to do higher powers. For example, if I wanted to do 1 plus 3i to the 10th, de Moivre's theorem will let me do that very quickly. If I wanted to do the 10th root of I, something we really aren't able to do at all, based on what we currently know, I can also use that theorem to do that very quickly.